show you what that is. I'm sorry, I'm just turning stuff off here. If you go to the course schedule, if you go to a website and you click on courses and you go to schedule, you'll see the schedule. Oops. And you can click on this, and then it'll take you to a page that looks like that. One day it might have a video here, but that's in the future sometime. And then you can click on that, and that'll take you to this page, and that's where we're going to get started. And what this is a tutorial that somebody else wrote, which is really great and is nicely defined. The way they describe this is it's very opinionated, but I happen to agree with their opinions about things. I think they have good opinions, these people. So I'm gonna follow their opinions. The nice thing about this is that it's really nicely written, so you can go back and refer to that. And we'll go over some of these things together, and we'll see how far we get. The overall idea is that in a lot of the work that we do, we end up writing a lot of sort of scripts, one-offs, notebooks, and one of the things that I think that many researchers, one of the questions that many researchers have as they're doing the work is, when exactly do I start making tools that are reusable? I'll tell you a little bit about my own workflow. Is that I work a lot in the notebook. I'm very used to it. So it's an environment that I feel natural in to write code and to explore data and so on. I enjoy that. And as I work, I start seeing some patterns, some code that I'm writing again and again. And then I will say, oh, this is a function. This is probably a function. And then I write a function definition, put that at the top of the notebook. And then as I run, I replace all the places where I wrote the same code with the call to the function. But eventually, I want to use the same idea in some other notebook. I want that function to go somewhere to some common set of tools that I can reuse. And what I will often do is I'll write a little Python file. So I have a repository. I'm working in this repository. There's a bunch of notebooks in there. I'll write a function called tools.py, and then I'll import from this tools.py into that notebook, in all the notebooks in that repository. That you can see already where this is going. This doesn't work well, because what if I'm working on another project and I say, oh yeah, there was this great tool in this other repository. So I end up maybe copying it over. That's not really a great practice, because now I'm starting to change it over here, and I need to change it over there as well, and so on. And I start writing testing for these things, and it starts getting out of control. And this might be a situation that and the question is, okay, so what is the next thing to do? And this is the starting point of this tutorial that we're going to do together. So we're going to start with some code. It'll be fairly simple scientific code that does something. And we'll start with setting up the structure for a Python package. One of the benefits of the package is that, now it's installed on your machine system-wide, and it's installed in the same way that, say, NumPy or Matplotlib or other Python packages are installed on your machine. So wherever you import this thing, you get it into your projects. But also, once you start doing that, the code is ready for you to give to others and tell them to install it, because we'll put together the installation machinery that Python has to allow you to give this to others. And eventually we'll get to the point where you can put this package that you've created up on the Python package index, so that others can install it, not only by downloading your code and running a few commands on their machine, but actually by typing one single command, pip install name of package, which is the way that we install a lot of the packages that we use. And it'll make the reusability of your code much easier. So we'll talk about all that. And then along the way, we'll because, as I said, this is an opinionated tutorial, we'll do a few things that are not necessary for all this to work, but that are good ideas. And you've heard a lot of this before. It's testing, it's continuous integration, and other things around that, documentation. So we'll add all those things into your little project, so you can follow along. I'll start from scratch over here, and then you can follow along and do everything that I'm doing. So what you'll need to make sure is if you're not in the Jupyter Hub, you will need to make sure that you have a few things. So I'll start actually by opening a terminal window here. So we'll start working in the terminal, and I'll close this files thing. So I'm in a terminal. You can be in a terminal in your machine. You can be in a terminal on Jupyter Hub, and we'll want to do all of our work. All the work that we do is going to be done in. We're going to try to isolate the work that we do in here from the work that we're doing elsewhere. So one of the things that starts getting really, really tricky when you're starting to do this kind of development is that you might depend on a certain version when you're working on a certain version of NumPy or a certain version of some software, and you want to be able to isolate your environment with that version of NumPy from all the rest of the work that you're doing on this machine, maybe with some other library that depends on some other version of NumPy. And there's a really nice tool to do that in Anaconda. So when you installed Anaconda, you installed along the way a tool called Conda. So you can verify that you have that tool installed by typing Conda. And I'll type clear to clear that. Is that font size large enough for you over there? Yeah, that's good. Okay. And so we can. I'll show you how you create a new environment. That'll be sort of a little isolated piece of your machine where you can, if you import stuff, it's imported within that context. It doesn't bleed over, stuff doesn't bleed over from other things. So I'm going to do conda create -n. Let's call it package. So this name package is an arbitrary name. Doesn't have to be package. It can be whatever the name of something that you'll remember, so you can come back to it. And I'm going to say, well, do this with Python. We're going to do all our work here with Python 3.6. And that will be, I'll just start this environment where the only thing that is in this environment right now is Python 3.6, nothing else in there. And as we go along, we'll install all the things that we need into this environment. So it's doing this thing where it's spinning around and trying to solve this environment for me. What Conda does is it looks at what I asked for. I could have asked for more things. I could have said Python 3.6 and NumPy this and that and so on. And it would have figured out what all the things are that it needs to install into that and sort of creates all the machinery for that. It tells me I'm going to install these things. Should I proceed? And I say yes. And it goes and it downloads and extracts these other packages, including, you see, Python 3.6.6 is what it's downloading there. It's installing a variety of different things, and this creates for me the environment. So it's downloaded a few things that it needed, and it's isolating that. And then so it's telling you at the bottom here, it's telling you to activate this environment, use source activate, and then the name of the environment. In this case, it's package. And you can see that the prompt changed. What's one of the nice things about this is that the prompt will always tell you what context you're working within, that we're working within the context of this environment. And if we wanted to go and go to something else, we could go back to our sort of base environment by typing source deactivate. And that would then deactivate this and take us back to our original context. But for now, we're going to stick around here. OK. The next thing that we need to verify that we have is we're gonna work all throughout this tutorial. We're gonna work with Git. We're gonna integrate Git into our workflow as we create this package. So typing Git just to verify that it's there, and indeed there's Git installed into the hub, so it's there. Okay. Next, we're gonna install another package that we're gonna use to create our own package, and that is, we're going to use pip to install that one, and it's called Cookie Cutter. Pip install Cookie Cutter. And when I type pip install Cookie Cutter, it goes and it looks for all the dependencies of this Cookie Cutter business, and it installs all of those, and it gives me back my prompt, and so now I have this tool called Cookie Cutter. And now we're going to use this tool. So Cookie Cutter, what Cookie Cutter does, it's kind of a nice tool. It creates, it's a software package that allows you to specify how you want to arrange other software packages. and then you can point to somewhere where somebody has specified what the organization of a package should be like and has some starter files there. And if you type cookie cutter that address, then it will create a directory that has all these things. It's like a cookie cutter, but it's like a cookie that you've created inside your environment that has sort of the start of a package. And there are many of these cookie cutter add-ons that give you different kinds of projects, and we're going to use one particular one that is opinionated but agrees with my opinions. So where are we? We're in our home directory. I'm actually going to make a directory right here in my home directory, and I'll call it source. That seems like a good, so this is a place where I put source code, and I'm going to put the source code in here. So I'm typing cookie cutter, and then I'm going to put this address, https://github.com/ and this is going to be weird, nsls-ii, and then scientific Python cookie cutter. So I'm running the cookie cutter program on this GitHub address. What this will do, it'll create a directory in there and it will populate it with whatever they put into that cookie cutter of theirs. This is the group that created this tutorial that I'm running and created this cookie cutter, and I think it's really great. So we're going to go with that. Does everybody have the address? Okay, I'm going to go ahead and run that and see what happens. Okay, so it starts by asking me a bunch of questions because it'll populate things inside my directory based on the answers to these questions. So I'm going to tell them that I am Ariel Rokem, and I'll give them my email. Maybe I'll give them my UW email. I'll give it my GitHub username, and then I need to choose a project name. So it'll ask me for several different names. Project name can be something sort of general, like excellent. Doesn't have to necessarily follow. Speaking and typing at the same time is hard. Excellent science is what I want to write. It doesn't necessarily have to follow any particular conventions. It's just a general project name. And then, so here it tells you this is going to be the package distribution name. And distribution name does have to follow certain conventions. Ideally, it'd be like words separated by dashes. So it'll be, for this one, it will be excellent dash science. It can be also just a single word if you didn't have several words to your title. So I'll do excellent dash science. And then it tells me the package dir name. That's going to be the thing that when you type import something, that's the thing that you're going to import. And in Python, for you to be able to import a name, it cannot have any kind of punctuation in it. So you can see that this one is written with this snake case underscore. So let's call it excellent. Just the short name, excellent. But you could have written excellent science like that. That's fine. This is fine. But this is not fine. Python doesn't know how to import something that has a minus sign in the middle of it. So, okay, so there we go. And then the repo name, I'll call the repo. So this has to be a name that GitHub would recognize. I'll just go with this excellent sign. Well, maybe I'll go actually. Oops, sorry. Just for consistency, I'll go with a dash here, science, like that. Okay. Project short description, Python package for doing science. That's the default, and it's just spot on, so I'll go with that, so I just type enter. Year 2018, and then it asks me what's the minimum supported Python version. Let's pause here for a second just to say that in this day and age, I think it's very safe to not support Python 2 anymore at all. If you're starting to do some new work and nobody depends on that work who's depending on Python 2, if there's no compelling reason to use Python 2, don't use Python 2. So there we go. So it's done doing whatever it does, and now I can look at my directory and I see that it created a new directory inside of here. Let's go into this directory, source, excellent, science, and take a look at what it created. So maybe I'll do ls-f. ls-f shows me which are files and which are directories. So you can see that it's created all kinds of files in here, and these are sort of the backbone of my Python package. So I have an authors.rst This will be used in order to identify who are the authors of the package. Right now it's populated with my name and no one else, because that's the only person. There's a contributing file. You remember Christy mentioned contributing files yesterday, so it's a good idea to have a contributing file in there, because GitHub will recognize that this is a file that tells people how to contribute to your package. So it's good to start your package up front with this thing. Docs contains the machinery to create documentation for your software. We'll look at that in a little bit. License contains a license. If your code does not have a license on it, then you've retained the copyright to this work, at least according to the laws in this country, and nobody else can use your code. So if you want other people to use your code, put a license on your code telling them, no, you can use this code under the following conditions. Ideally, don't make up your own license unless you're a lawyer and you know what you're doing. Use commonly used license. Let's see what they used in here. So I'm going to type it to the screen. This is, they've given themselves, Brookhaven Science Associates has gotten the license to the copyright to this thing. That's interesting. I would have expected them to insert my name in there, but they didn't. That's kind of nice. It's actually a clever trick there. I think that's accidental. And then there are a few sort of conditions to this. I recognize this looks a little bit like something like a BSD license or an MIT license or something like that. Maybe a BSD 3 clause, I think. It just says, you can do whatever you want with this, but please retain the copyright. If you're reusing this code, retain the copyright. Just pass it along. You can pass this along, you can sell this if you want, but when you do that, just put our copyright inside the code if you're going to reuse our code. And then, there's no, this is the part where you apparently need a lawyer. This is the part that tells people that they can't sue you if they use your software and something goes wrong. And that they can't use your name also, the name of your university. So, but put a license and use one of these licenses. I regularly use MIT or BSD for projects that I use. One of the nice features of these licenses, in contrast to other open source licenses like GPL, is that it doesn't have an infectious characteristic to it. So, for example, if somebody depends on your software but doesn't actually copy over your code into their code, they don't have to use the same license that you use. They can, for example, they can say, no, this is commercial code. You can't use it unless you send me an envelope with $10. Then you can use I'll give you a license to use the code. If somebody wants to do that with software that I've written, it seems fine to me. That seems like a good enough use of my software. GPL won't allow you to do that. You'd have to use the GPL license. So, okay. Okay, so we've done all that. Okay, license. So next is manifest.in. That's sort of like a metadata file that will tell Python what are some things that go along with your software. There's a README. Having a README here from the beginning is a good idea. There's a requirements file. You saw requirements files in Fernando's talk. A requirements file tells installation machinery like Binder, but like pip also, what are other packages that are required if you want to run the code that's in this package. You'll notice that there are two files in here for requirements. One is called requirements and the other called requirements-dev. And that's because often there are differences between the kind of software that you need in order to develop the package and the kind of software that you need in order to just use it. Because we're going to rely on all kinds of other software here to build the documentation, do testing and things of that sort. And your users don't necessarily need to run your tests or to build your documentation from scratch when you're using your code. And then there's this setup file. Setup is a really important file in here. It's a convention that every Python package should have a file called setup. And that file is the file that contains instructions for Python how to install this package, how to build it, how to install it, how to put together everything. So this file is really important, and we'll take a look at it in a little bit. And then there's another one called Versioneer here. Versioneer is a project that we've kind of plopped in here that handles versions of software nicely. It can, for example, let your users know if they're using some version that is not the release version of your code. It can tell your users exactly which git commit their software, the software they're using on their machine comes from. So there's a lot of machinery inside of that one file called Versioneer, just for handling versions, and we let Versioneer handle that. What else? Oh yes, the package itself. So it created inside of my directory called Excellent Science. It created a directory called Excellent, and that's the directory that's going to contain the code itself. We can look at what's in there right now. It has tests directory, I believe, an underscore version file, and a double underscore init. Sometimes when talking about Python, because there's so many double underscores, we just say dunder instead of double under. So if I use dunder, if I go and say dunder, I mean that double underscore there. So the dunder init file tells Python that this is something that it might be able to import. And when we type import excellent, in this case, if I type import excellent, once I've installed this, if I type import excellent, that dunder init file will get run actually. And if something needs to happen upon import, it'll happen within this, at that time. Okay. I will point out that there are, in addition to the files that I've showed you, if I type ls-a, there are some additional files that are hidden in here. There's a flake8 file in here, there's a git attributes file, and a git ignore file. Who here has seen a git ignore file before? Okay, so a lot of you, and I'll just say in there we'll put stuff that we want Git to not version for us. And I believe they've already populated it with the stuff that we, yeah, they put in there stuff that, you know, is like cruft that if we add it to our Git, it'll just be annoying and we'll have to remove it. So it's ignoring it for us. Flake8 is a software that checks that the code is nicely written, that there isn't, for example, cases where we import something but never use it. That's the flake part of it. And then 8 stands for PEP8, which is the standard for writing Python, nicely written Python code, and there are tools that automatically check that. That file configures how those tools are going to operate on our package.
Sorry, why did you put everything in source?
That's how I organize things. I don't want to put like stuff that I'm working on right in my home directory. Right. Instead, I create. That's actually a very idiosyncratic personal convention that I have. That I have a directory on my machine called source that has source code in it. The nice thing about having a source directory is that I can go in there and I can delete that entire thing. And there's probably somewhere else that this exists, usually on GitHub. So if there's something I cloned from GitHub, for example, I clone it into the source directory. I have another directory. This is just like my idiosyncratic workflow. I have another directory called projects. I'm much more careful with the projects directory because it might include stuff that I haven't yet versioned or includes data in it or stuff like that. Does that answer your question? Yeah. Okay. Okay. So the first thing to do right before we do anything else is git init. Git status. So it's telling me you've started stuff, but you haven't added anything into it, and I'm just going to add star. I'm going to add all of this into my Git repository right off the bat. I didn't do really anything. I've created all these files with cookie cutter. So I create a commit right here with everything in it, so that if things go wrong, I can always go back to the starting point. Git commit -a-m initial commit of cookie cutter template. So like this will tell me, okay, so it created this mode, it added all these files. That's good. Okay, cool. Let me go to GitHub and there we go. New. I'm going to create a repository for this. I believe I called it Excellent Science. Fortunately, I haven't done this before, and let's make it private. The important thing is not to initialize this repository with README, not to check that box, because we're going to create an empty repository. We're going to push into that repository everything that's on our machine right now. So I create this repository with nothing in it. This is what it looks like when you first create a GitHub repository, but you haven't put anything in it yet. This is what it looks like. It actually gives you some instructions for what you would do if you already have an existing repository, which we have, right? We created something on our machine. So I'm going to copy this URL from my repo, and I'm going to tell it that I want to git remote add origin and then the URL. So this command is very long because that's how it goes with Git. So git remote means that I'm dealing with remotes here. Add means I'm going to add a new remote. Origin is the name of that remote. It doesn't have to be called origin, but it's a very strong convention that this one would be called origin. And then I give it that address, and that makes Git know that now there's this remote. And then git push origin master, which is the branch that I'm on right now, will ask me for my credentials. And then push it up. Great, okay, so it's created a new branch. There was nothing there before, but now all of these files are up here. Cool. Great, great. We can scroll down and see what's in the README. So far, there's not a lot. Under features, we have to do because we haven't done anything. Then it says documentation coming soon. It's telling you that there will be documentation at some point after we create it. It'll be in that URL, which is a nice URL for this. And then it actually does tell you what the license is. Free software, 3-clause BSD license. I've grown the ability to identify licenses by reading them. It's remarkable. Okay, great. So we've pushed this up, and that's what we're going to do, right? We're going to work on this, and then we're going to commit, and we're going to push, and so on. And everything we work on is going to be out there publicly available, and anyone can grab it and use it. That's pretty good. Okay, the next step that we're going to do is we're going to install this piece of software on our machine. There's nothing there yet, I know, but we're going to install this piece of machinery, this package, in a way that whenever we make changes, those would get updated in our installation. And we're going to use pip in order to do this installation. So pip install -e dot. And that -e there, so you've seen before pip install cookie cutter, for example. That went to the Python package index and pulled down cookie cutter onto your machine and installed it wherever Python packages get installed on your machine. Here I'm installing the current software, so that dot stands for this directory. I'm installing whatever's in this directory, and what pip will do is it'll look for that setup file and run it, presumably, and do stuff with it. And the -e stands for editable. So I'm going to install it in a way that I can continue to edit the software, and that will update wherever that's installed. It will get updated. And the way so it's done that, it's abstained, the way that works, the -e works actually is by linking wherever Python packages get installed on your machine. It's now created a link to the source code that's here. So whenever we update things, it's going to update automatically because it's linked directly to these files that we're changing. Yes?
Is this preferred to instead of typing like Python space setup.py space develop?
It is near identical to typing Python setup.py develop.
Okay.
That does something very, very similar to this. Yeah. So. Okay, and so we can go and we can verify that we can install this thing. Let me go home. So now I'm in my home directory, and maybe I'll go to this. I've created a temporary directory just for playing with things. I'm going to add a notebook in here, a Python 3 notebook, and I'm going to type import excellent. Oh no, that's not good. That probably has to do with that conda env that I created. So I'm going to scratch this whole thing with the notebook for now. I'm going to go back here, and I'm going to change my directory to my home directory, and I'm going to start a Python terminal. Let me do this. I'm going to start a Python terminal in here, and then I'm going to type import excellent there. And that worked. Okay, so inside the environment that we've created, we'll have to figure out later how to make that environment visible through the notebook. But for now, let's work in the terminal. So now it's possible to import. That's, by the way, another reason that I create another directory instead of creating that directory in my home directory, is so that I can always test. If my directory is in my home directory, it wouldn't be clear, am I importing from the stuff that's right there in my home directory, or am I importing from somewhere else? So putting it somewhere else is a good idea so that it's isolated in that way. Okay. Okay, we're going to go back to our CD source, excellent science. We're inside our repository again. And one more thing that we'd like to do before we move on is we're going to pip install -r the requirements-dev file. So pip install -r means install some requirements based on a file. I'm going to point you to a file, install everything that's written inside that file.
Sorry, is it possible that setup.py was set up written for Python 2? Because pip3 worked, but I'm installing with pip3.
You're running with pip3, and it works.
Because pip didn't work.
Pip did not work.
With setup.py.
Are you working on the hub or on your own machine? On your own machine. So it depends a little bit on what you have there on your own machine. Did you do the whole conda end thing?
I did the end.
Oh, okay. You have some virtual end kind of thing there. Okay, so you're using some other virtualization or environment isolation software, and things might get a little bit hairy because if you didn't install pip into that environment, then maybe it's pulling some pip from somewhere else, and there's a good XKCD comics. Oh, let me just bring it out back again. I suggest that you read this one. You have this on your machine somehow. It's sad but true. There's a lot of different ways to install Python, and some of them don't agree with each other, and then you get all kinds of a mess. So I can't really tell without going a little bit deeper into what you have there. At any rate, this went and installed a bunch of stuff that we need as dependencies for our next few steps.
Sorry, what was it?
I typed pip install -r requirements-dev.txt. So again, this file includes packages that you need in order to develop the software, but not necessarily to run it. So it separates away requirements for development from requirements for running it. Okay. So far we've sort of been setting up our environment, and now we're actually ready to start develop the software. So let's go into, where are we? So I'll clear the terminal. Whoops, that was not good. What did I do? Oh, I ran clear on that thing. Okay. Okay, let's hope that went well. But I'll run clear here so that I get this. Okay, so here I am, and I'm going to cd into excellent. And in here, there's not much, but let me create a new file in here. So creating a file is you can do that with touch, and I'll call it refraction.py. I'm going to do some optics. So we're going to have a module that is devoted to refraction. Let me open that file in a text editor. I'll go home and then to source, and to excellent science, into excellent, and I have my refraction file here. Okay, let's write some code. Okay, import numpy as np def Snell. I'm going to write a piece of code that implements Snell's law, which is a law of refraction. It's what happens when some light incidents on something like glass or like water or something like that. There's some laws that govern how it breaks. So this is called the refraction angle. So we're going to compute the refraction angle using Snell. Let me close this. Snell's law. Sorry, this is all inside of triple quoted block. A triple quoted block is a multi-line string in Python, and if you put it right after the definition of a function, then that multi-line string is going to be the doc string, the documentation string for that function. It's a good idea to write a nice and well-documented, some nice well-documented code. For example, here we're going to write what are the parameters and what they mean. Theta float incident angle in radians, n1, n2, float the refractive index of medium of origin and destination. Let's write some more here. Returns I'm actually going to call this alpha. And then let's go on and even write a little example. Okay, so this example is, a ray entering an air water boundary at 45 degrees. So this will compute the exit angle if a ray enters that boundary at 45 degrees. What will be the exit angle of that ray of light going in? Okay, good. So that's all the documentation. Now let's write the implementation. Return np.arcsine of n1 over n2 times np.sine of theta. Oh, I should actually gonna, yeah, okay, that's fine. Okay, so this is actually it. This is Snell's law. So it's pretty simple. It's basic optics. Cool. Okay. As you can see, the documentation takes up a substantial amount more lines than the actual implementation. That's not a bad thing. That's often the case when you're doing things that are sort of basic numerical stuff. There's a lot more handling of things than might change. It's not too important. The important thing is that your documentation includes everything that it needs to include. It needs to include a little one-sentence, preferably one-line description of what this function does. It needs to include a parameters block, which tells us what are the parameters or inputs into this function. It needs to include a returns block that tells us what the things are that come back from this. And it needs to include it should include an example. Hopefully that's really helpful for people who want to use your software and for yourself in the future. And the way that this is written follows a very specific, there's not an accidental character in here. This follows something called the NumPy docstring standard. You can look that one up. It's a set of rules that we follow when we write scientific software that follows the same documentation standards that the NumPy package follows. And the reason that's a good idea is that we can now, as a community, build tools that expect documentation to look a very particular way, to have certain sections, to have certain spacing between things, and so on. For example, it is no accident and an important fact of the world that there is a space before this colon and after this colon, and that is because if you don't do that, the formatting later on when we format this into some other format will be all wonky. So that ends up being important. And what's nice about this, it's written in something called restructured text, which is the same. Again, Fernando mentioned Sphinx, which builds documentation, which is the system that builds the documentation of the Python language. We use Sphinx as well, and Sphinx expects things like spaces. Sphinx is actually a rather finicky system. It really likes, like Python, it likes to know where its white space is going to be. So often when things go wrong, it's because there's a line space missing or a space between a colon and something missing. So this is all written in restructured text and then gets processed by things like Sphinx to build our documentation. Even if you don't follow these rules to their letter, I would recommend writing a doc string so that people know what to expect from this, and really so that you know 6 months from now when you're importing this function, you're like, wait, what came first? Was it the angle or the refractive indices? Which one was it? So Yeah, this is actually, I don't like this documentation. I should say I copied it, but now I understand that it's very ambiguous which one of these is the medium of origin and the destination. And in Snell's law, it actually really matters which one you put where. So I'd actually break that down into two different refractive indices just to say this is the medium of origin, this is the medium. So I have a pull request for these people coming later. Okay, good. In general, when we document things, we document by saying what is the name of the thing, and then what is the type of the thing, and then we might have a sentence or two describing in more detail, a sentence or two with capital letter, what this thing is. This should have a period at the end. Sorry. Okay, good. So now we've done this, and now if we look at this code, we see that we've added a requirement to our code. Now we require NumPy. We didn't require that before. I'll show you what our requirements file looks like until now. This is what our requirements file looks like right now. Yeah, it doesn't have anything in it. Let's add NumPy to that. So we write down NumPy in the requirements file, and that means that this is going to require NumPy. When people install it, it'll install NumPy for them if they don't have it. And we can go to the terminal and type pip install -e dot, which is again install this editable version of this to make sure that where am I? Oh, I need to be one folder up. Yeah, right where the setup.py is where I need to run this. And we'll see that it actually goes and makes sure that, did it go? I guess it has NumPy there somewhere from some other dependency, so it didn't install NumPy, it already had it installed. But I think if we do, for example, if we go home and we type Python and we import NumPy as np in here, then it finds NumPy. So NumPy is installed in this environment, and we can type even more. We can type from sorry, not example, mine's called excellent, dot refraction, import Snell, and it recognizes that, and then I can type something like Snell np.deg to rad 45 degrees from air to water, and it'll tell me the answer that I expect. Yes. Cool. Okay. And then we can, in the standard Python shell, we can type help Snell, and it'll type the help document, the doc string that we wrote in here, including the example and so on. That's nice. Okay. What questions do you have so far about any of this? So this is, now you have, this is it basically. Now you write code in there and everything works, right? So it's the start. Yes? Yeah, that's actually a good idea to do, is to sort of look. I know this works under version, so this under version is an attribute that this has. 115.0, I know it works with that one. Maybe I'll just pin that as my requirement. And you can pin the requirement by doing equal 1.15.0. And this is a really good idea to do that and to check what the requirements are. Every once in a while, when a new version of NumPy comes out, you might want to update this and check that it still works. And then update. Yeah. Yes?
So I know in some packages you could do import, say, excellent, and then you can do excellent dot refraction dot whatever function you're searching for.
Yeah.
What determines because I don't think that'll work in this case.
Let's try it. I'm not going to.
Try to access the method.
Let's try. Okay, so I'm.
Here.
Oop, where am I? Oop. What happened?
I just don't know, like, what's the syntax that determines the difference between, or what about the.
Exit and there we go. Okay. Python dash. Let's just do Python And then we're doing import excellent as ex, because ex is good. And then ex.refraction.snell is what you're looking for, right? And you can't find that. It says I don't have this thing called refraction. And the tricky bit here is how do you do these imports and how you set things up. And that's done by that dunder init file. Right? If we wanted, so the general term that you're looking for here is namespaces. And the question is, how do you set up namespaces? So namespaces are a great feature of Python, this idea that you have something, and inside that something there's a bunch of other names, right? The way that we, inside of snell.refraction, we might have inside excellent.refraction, we might have a function called snell, and we might have another function called something else, and so on. That is the namespace, the refraction namespace inside of the excellent package. And sometimes we refer to that refraction also as a module, or we might have sub-packages. Those are slightly different things, but not that different. And it depends to some degree, at least, on how you set up things inside of like I said, that this dunder init folder. So as you can see, it doesn't import anything into that namespace, right? I mentioned that when you import the package, when you type import excellent, it runs this file. If you had set up things so that it does something like import what was it, refraction. In fact, import dot refraction. Like from here, import this thing called refraction, it would have imported that name into there and we would have had that. We're going to be opinionated and not do that. So we're going to say, let's treat these things as separate things. You never import excellent just by itself. Instead, you're going to have submodules in there and you're going to import those. I'll go further about sort of design in a little bit, but maybe I'll say something about that. What they recommend in this tutorial, and it seems like a really good idea, is not to have like really nested hierarchies of things where you have like from excellent.refraction.snell.blah blah blah import the function and so on. It just gets really hard to know what you're doing. Instead, having a relatively flat namespace is a good idea as long as your package is not like super enormous. Yes?
So before we created the refraction file, we had installed excellent. And
Yes.
So it was empty, but we added the -e flag.
Yeah.
Under the with the caveat that was basically saying that we can edit it.
Yeah.
We have to install it each time.
No, not really. I did do that again, but I probably didn't need to do that. Yeah, I understand why you're asking, because I went and installed it again. It was like, why are you doing that? And that makes sense. I think, so let's test that idea by doing the following. We'll define another function in here, and we'll call it, I don't know anything about refraction, so that's the problem, except for Snell's law. That's it, I've run out of things. So let's do like refractionary. That'll be another function, and it passes for now. It doesn't do anything. And I'm going to go to the terminal, and here I am, pwd. I'm in my home directory, so start Python, and from, what was it, excellent.refraction import refractionary. That's not a problem, right? And I didn't need to install it again. So yeah. Right, and that's the whole idea behind this -e flag, is so that I can keep doing that. I could go and edit the code and reload the import. This is a quirk of Python that will really ruin your day if you haven't used Python before, is that once you import a package, Python is going to be lazy, and even if I were to write this thing, import this thing again, it won't do this unless I reload the entire thing. So I need to do something like from import lib import a function called reload. That's a standard library, and then I can do something like reload. Actually, I need to do import excellent, and then reload excellent. And only if I actually tell it to reload is when it's going to import it again, as long as I'm in the same session. So when I work in the notebook, often I won't do this. Instead, what I will do is I will restart the kernel every time I update the code and rerun everything if it's a very long running thing, it's kind of annoying. I just ran like 5 hours of some data preprocessing and now I changed my function, then I need to do that. Yeah. Yes?
So for, let's say for like functions or scripts that you use a lot for many different projects, you usually create them as packages so you can call them from anywhere? Or?
Yes. Yeah, for a lot of stuff that I do, I end up create one and use it everywhere. That's really what I'm trying to drive you towards here, is to do that. It's really a good idea, because otherwise you end up saying, oh yeah, I had this utility, it was really great, and ultimately what I'd like you to, the mindset I'd like you to have eventually is, oh, I created this really useful tool. It might be useful inside of Nebabble or Nelearn or DiPy or in NumPy, right? I created this great thing. It does this great thing with arrays. I'll go and contribute it back to NumPy, and then you won't have to worry about maintaining it anymore. It'll be in this community maintained package. But that's once you've hammered it out. Yes?
So when you, let's say you want to contribute, or let's say you want to branch out from an existing package, and you import the license, and it says reuse this license, what does that mean? You just copy it and just use the same.
So that clause in the license about like if you're using this code is, I'll give you an example. In DiPy, I developed a software package called DiPy. It does diffusion imaging, and we were using some code from another package called scikit-image that is released under the BSD license. And we literally took and copied a function. We didn't want to depend on scikit-image because we wanted only this one function. And we wanted to make changes to that function also, so it was even more complicated. So we copied that one function into our source code. And when we copied that function, we also copied into the same file the entire license of scikit-image, the whole thing.
In your license, and then you added stuff?
So we took that license and we put it in the same file in which we had the code. And we said, this is the license. So we actually wrote, this was actually in the docstring. So in the docstring we wrote, hey, we took this code from scikit-image. Thanks to scikit-image. Here's the license for scikit-image. And then, so okay, we've given them now the credit. And so anyone who uses our function now knows, okay, that actually came from scikit-image. And these are the people who made that. And then we're free to also go and make changes and so on. And nothing in the license says that you're not allowed to change the code. In fact, I think it says explicitly you're allowed to change. So, okay. Good, okay. The next thing we'd like to do then is, so we've written a little bit of code, and this is a good time for us to make sure that it does the right thing also, which is a good idea. So we're gonna start writing some tests right off the bat. And the test driver that we're gonna use is called PyTest. This is, again, not an accidental choice. It's really one that I would recommend using over others. So I'm going to go to source excellent science, and I'm going to run python-m pytest. What this does is so pytest is inside that requirements dev file. It's mentioned in there, so it should be installed here. Python-m pytest, what it does is it kind of imports that module. And when you import this particular module and run it in this particular way, it kind of runs the test driver. It runs the tests. So what happens when you run pytest is it looks into your source code. It looks into that tree, wherever it is running. It'll look down that entire directory tree, and it'll look for files inside there that have the word test in their name. And inside those files, it'll look for functions whose name starts with test. Right now, actually, inside of here, there is a folder called tests. So inside here, it'll find this test examples, and it will run the it'll run this test 1 + 1 is 2 function when we run the tests. And this one is clearly, if this doesn't work, then we have to rethink everything. So this is better work. So the way to read this is called an assert statement, and this is the thing that it is asserting. It's asserting that this should be true, and if that is not true, if this logical state, so this should be a logical statement. If this is not true, this will raise an error. If it is true, it won't do anything actually. It will just keep going. And the way that PyTest works is it looks and it kind of keeps tracks of errors as they show up. It doesn't stop running when an error happens, but it just kind of keeps tracks of these errors so that it can report to you in the end an error happened. So let me show you how that works. So I'm going to run this, and there it ran test examples. Let's just show you what happens if we assert something else. Instead, I assert that 1 + 1 = 3 instead. Seems like that shouldn't work. So I run that again, and it comes back and says, yeah, that's bad. Right? So it ran through everything. There's only one here. It tells me I ran this excellent test example thing, and one test failed in there. If there were multiple functions inside that one file, if there were multiple functions, I'd get like a dot for every one that passed, and a letter, either F or E, for every one of the failures or errors, respectively. And it actually points me to the exact line where the assertion failed. It says this is the thing that didn't work for us. So let's go back to the real world, and that's okay. We have tests, good, cool. Okay, so let's ask that a test for our code. Okay, so we'll go into the file. Where are we? We'll go into the files inside of tests, and I would like to add a test. I guess I'll add a test right in that same file. So def test perpendicular. So it turns out that if there's no incident angle, then you expect there to be no refractive angle as well. It's supposed to go in the same. If it goes straight in, it'll go straight down into the water, for example. So we're running our Snell function. Oh, I forgot to import it, so let's put that at the top. We'll import numpy as in p, and then import, from .. import Snell. This is called a relative import. It says, go up one directory from where you are, look around, is there something called refraction? Look in there, grab me Snell from there. We could have written just as well from excellent X.
I thought you could call it from anywhere.
Say that again?
I thought we could call it from anywhere. Remember you went to your home directory?
Yeah, we could have written from excellent.refraction, and that would have been like running it anywhere. In this particular file happens to be inside the same source tree as the refraction file, so you can tell it, oh, wherever you are, go up one directory, look around, find refraction, and grab Snell from there. So you can do this relative import. You can argue forever about the merits and demerits of using relative versus absolute imports, so I'll avoid it here. I personally like absolute imports, but there are a lot of benefits to doing this as well. So let's leave it like that.
Why would we need to import numpy if it's imported within Snell?
Well, we'll use it in here also. I'll show you in a second. So that's one, test perpendicular, and then let's just make sure that this is not something weird about the conditions we used in particular. Expected equals 0. It doesn't matter if we do 0, 2, 3 or 0, 3, 2. It doesn't matter the relative refractive indices of these two media. It doesn't matter. It should always be 0. And then here I'm assert that actual equal expected. And this is sort of the pattern that you're always going to use in what are called unit tests. You're always going to say, I calculated on a piece of paper that, Snell's law, when it goes, there's no incident angle, it's just supposed to be the answer should be 0, so my expected is 0. I've calculated using my function, and I want my actual and my expected to be the same. That's like a very, very typical pattern. And that's the pattern that we're using here for the unit testing. So okay, so we did this, and then let's write another test in here. Def test air water, and air and water equal 1.33. So this is annoying syntax. I'll stop it because okay. And air is 1 and water is air. I'm gonna run actual equals Snell with np.deg to rad of 45 and an air. And so I'm working through sort of a known case where we know what the answer should be. Expected should be 0.5605137424605. Yeah, I think I got all the digits in there. Very good. Assert actual equal expected. Good for us. Cool. Okay, great. So we've written these tests, and now let's go back and run them. 3 items. So that all ran fine. So everything's good. And just to go back and show you so this is where I used NumPy. That's why I needed to import NumPy. Was for this call here. Yeah. Right. And we can keep doing this, right? We can write more tests. In fact, if you run into a case where all of a sudden there's a bug, somebody emails you and says, hey, I was using your Snell function and I tried this case, and you figure out that there's a bug, it's a good idea to actually write a test first that fails because of the bug and then go fix the bug. And that's good because then the bug won't creep back into your code. In fact, if somebody emails you and says, hey, it didn't work for my case, I would encourage them to write a test that fails. Kind of demonstrate for me that this doesn't work in the way that is expected when you use the code in the way that was intended. Okay, what questions do you have about this? It's sometimes a good idea to put multiple assertions inside of one unit test, especially if there's some preparation code. Sorry, where is my... If there's some preparation code up top, if here there was like some long-running, I don't know, not long-running, but something that creates some data and so on, and it's not a bad idea to put multiple assertions into the same function, so that's often done. But you want to create separate test functions for every kind of behavior that you're testing, right? This really, the way to think about these functions is this is a behavior of this feature. This is what happens when you run it on perpendicular angles. And here we've run it twice with perpendicular angles with different kinds of media. And this is a particular known physical kind of thing that we know the answer. Okay, good. Okay, so let's move on to the next thing. The next thing that I'm going to show you is how to lint your code. So linting is a term for sort of cleaning up your code, making sure that it's sanitary, and we do that using Flake8. Sorry. So I mentioned Flake8 a while back. We're going to run Flake8 here. So Python-m Flake8 does the same thing that Python-m PyTest does. It runs Flake8 on the current source directory, and it checks it for linting. So it's actually failing quite miserably because there's a lot of different things that went wrong. This is interesting. So apparently I have some ipynb checkpoint folder in there that has, yeah, it'll have a lot of problems, a lot of issues with Ipython notebook checkpoints. Really, the one that I'd like to look at is here. So there's a lot of issues with the way that I wrote this. Like having all these breaks here is not considered good code hygiene, so we should probably get rid of that. And there, between functions, according to PEP8, there needs to be 2 white spaces. And before this function, we probably need 2 spaces as well. So now I've rewritten some of these things. I seem to have some extraneous white space at the end of rows also, which is annoying. Here, for example, I have some extraneous. Here I have a lot. Okay. So I'm going and cleaning up. I kind of took a look at what it said was wrong with my code, and I can keep going and doing that. So test examples, line 9, blank line contains white space. Oh, there's a blank line with white space. Yeah, this has white space. This has some white space. So you can see Pepe is going to be really, really strict with these kind of really annoying things that you can't even see.
Do you know of an easy way to open the gitignore file in JupyterLab? Because it's like a hidden, has a dot with it.
Yeah, I don't know why we have this IPyNB checkpoints thing is here. It might be something that I did, but it might actually be in the cookie cutter. More pull requests for the.
And mine too.
Hmm?
When I saw those, I have that folder too.
Yeah. So okay. So let's go and edit this thing. So okay, I'm gonna edit it here on this because it's gonna be hard to find it. Let me do this. So PWD, we're in here. LS. I'm gonna use nano to edit this gitignore. And I really think that we should have, this is distribution packaging, PyInstaller logs, blah, 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 blah. Oh, it's supposed to ignore it. Oh, you know what? It's supposed to do this. Otherwise, why would it ignore it? I think that's the thing that was missing. So okay, it did have a good call on them on putting this Ipython notebook. So Ipython notebooks create a lot of these backup files inside something called IPyNB checkpoints, and they're just really an eyesore whenever you're working inside some directory with Git, because all these changes inside of these checkpoints will appear, and you don't care about that. So ignoring them is a good idea. What they had was this, which doesn't ignore the files inside the folder, but this will ignore the files inside the folder, I believe. So.
Can you read the gitignore file too?
Hmm?
Does Flake 8 read the gitignore file too? Or,
Sorry, I missed that again.
oh, sorry. So was running Flake 8 also use the gitignore file?
No.
Which files to ignore?
It won't help us for that, I believe. Although we do want to. Oh, actually, I didn't. What I was doing. Yeah, no, I'm completely wrong, and I'm doing the wrong thing here. This probably worked just fine, the way it was. Maybe, probably. What I really want to look at is this nano.flake8 file. This is the file that we care about. So this tells us what to exclude. This is where we set what to exclude. Okay, so it's going to exclude our Git thing. But maybe let's add the slash dot IPyNB checkpoints in here. Maybe that will do the right thing. Yeah. So now I see nothing that has to do with that. Instead, I have a bunch of stuff that I did inside of the code itself. So you go and clean up all these things. You see a lot of it is like white space. In fact, all of it is white space. So it asks for all these white space changes. So we go and clean those up. Let's not do that right now. Instead, let's go and so we've done a piece of work on this thing. We're pretty happy. The tests are passing. Flake 8 is passing. Let's just assume that for a second. So we can do git status and check what the situation is like. So there's changes that have happened to these. Okay, there's this untracked file that we've added. Excellent/refraction, and then we made some changes to the requirements, we've made some changes to the tests. And so a good idea is to, when you're sitting there and you're looking at this and you're like, wait, what branch am I on? Oh, I'm on master, is to say, oh, git check out -b add Snell function. I'm adding a new function here. And then it takes us on to another branch in our Git repo. And in this branch, we're going to make our commits. Well, first add stuff, git add excellent/refraction, and git add excellent/tests, test examples, and then git add dot flake 8. So on my initial adding, it didn't add all these hidden files, because when you do git add star, it adds everything except for hidden files. So I'm going to add those in here as well. I should have added them initially, but I didn't. So maybe I won't add them into this same thing. But okay, so I have everything that has to do with this particular branch. So I've added that. So git status. I'm going to keep these unadded things. Oh, I want to add git add requirements, because that actually requirements.txt, because that actually does have to do with the changes that I've done here. So it's added everything, and now I can do git commit -a m and add Snell function and tests. Good. And then git push origin add, what did I call this branch? Add Snell function. No. Okay, good. So now there should be a new branch with that thing. And then you keep repeating this. You go and you edit more stuff. You add to this branch. And then you can go to GitHub and make sure that that things are behaving as you wanted them. I'm going to skip over a few things here just to go to the point where we're going to turn on continuous integration for this and sort of look at how to set up continuous integration, because I think that's kind of a nice feature that we can do here. So I'll point you to this file that we have here. So I'll check out the master again. That doesn't have any of this new feature. We'll come back to this feature a little bit later. We'll make a pull request to make sure that things are working as they should, and so on, once we turn on continuous integration. I will add .gitignore, git and .flake 8. And what else did I have there? Git status and git attributes, and most importantly, git add travis.yaml. Okay, so this travis.yaml file that I just added, and I'll say git commit -a m add infrastructure files. That'll cover what I just did. Git push origin master. Okay, so we've updated master with these new files. Let's look in particular at, .travis. Let's look at a little bit more at this Travis file. What this Travis file does is a configuration file for this system called Travis. It's very similar to the one that you saw yesterday in Circle. Again, this is opinionated, so we're using Travis. What this does is it tells Travis what kind of environment to set up and how to set up all the things in this environment. So it'll set up the language for this. It'll be Python, and we're only supporting Python 3.6, so that's the only environment you will test on. If you want to test on others, you would add 2.7, for example, here. But we're not going to do that because we're not supporting 2.7. But any kind of version that you want to support, you'll put in there in this, and it'll spin up several machines with all these different things that are in that. It caches certain things just to make things go faster, and then it does the installation, right? And installs pip install dot means install this thing that we're creating, and then pip install -r requirements dev will install all the development requirements that are required for testing of this thing. And then we're going to run pytest and report on the coverage. Coverage is how much of our code is covered by our tests. It'll report that. It'll upload the report to another website called CodeCov that tells us how coverage is and reports to us back whenever coverage changes. And then we'll go with Flake 8. They've decided here to enforce code style but relax the line length limit, which seems like a sin to me, terrible. The PEP8 requires 80 characters of code and no more per line, which is a really good idea in my opinion. So doing that seems funny, but okay. And then it builds the documentation. So at the same time that we're testing the code, we're going to make sure that the documentation builds cleanly, that we don't get any errors out of the documentation build, because who knows, when we change something in the code, maybe we broke the documentation build in some way. So we're going to just make sure that whenever we change the code, everything works, including the documentation build. So that's this file here. I'm not changing anything in it, so I'll just exit. Save modified buffer, no. No. And then let's take a look at how we activate this, this thing. So Travis-ci ci.org. Like that is where Travis is. And it opens on something. It has my repositories. In your case, if you don't have repositories, it'll show you something different here. It's not too important because we're going to head off to. So you'll have to at some point authorize, link up your GitHub account with your Travis CI account. At some point, it'll ask you for permission to do things, and you'll have to do that. I've already done that, so you'll never see that on in my case. Okay, let's go to my repos, me, and what are we doing? How do I get to the repos? This always confuses me. What does this have to do with, oh, here we go, my repositories. Plus, maybe that's what we're looking for. Okay, yeah, I think if I go here to click on this thing, click on my name or face or whatever that is, it'll take me to the right place, which is right here. And now I can say sync, and sync will grab newer data from GitHub. So it needs to sync with GitHub so that it knows about the most recent stuff that I've done on GitHub, including creating this new repository and so on. And now I can try to find that repository. I'm just going to use the command F, or like the search function in my browser to find excellent, and it's not there. Oh, because it's not. I made it public, but I have so many repos all called 2000 something that it's going to be not on this page, but it's alphabetically ordered. So we're going to have to wade through all my A repos, all my B repos, all my C repos. Oh, there's Z. Oh, I clicked on last. That was not good. So that was the Z. Oh, here we're in R. Oh, sorry. Sorry, you know, some people store things on their file system. Why, I say, when you have GitHub. So my file system is all there, so there's a lot of it from from years of file systems. It's not only this laptop. Oh, here we are. Okay, good. So we're in this repo, and it says this is not an active repository, and we'd like to activate it. So let's activate it. Cool. Okay, great. And so there's nothing in the build history. Nothing has happened yet. It's been activated. We don't know anything about it. There are no pull requests, no branches to look at. Really, nothing has happened yet. But we're gonna make something happen. So next time a pull request is opened, this will trigger the run of this continuous integration, and we know exactly what to do that because we just okay, excellent. We actually just pushed some code in this add snell function, so we can create a pull request out of that. So we're going to create a pull request out of that, and that will trigger the CI build. Okay, so that created the pull request, and because I set up Travis, I should set up, oh, there it is. So because I set up Travis, it'll say, oh, there's some pending checks, and there'll be like this orange thing here. And that lets other people, let's say I have them collaborating with others on this repo, lets other people know that we have to wait and see what Travis says before we go ahead and merge. Or we can go and check on the Travis build. It'll take us, if we click on that orange button, it'll take us straight here, and we can see the build as it's happening. So it's going, it's installing NumPy, which is the required, so we went and installed the requirements, uninstalled it for some reason, installed a bunch of other things. It's installing all my development requirements. This is fun to look at, of course. So one more thing that we, if I remember correctly, we haven't really done in our Travis configuration, but maybe we, here, it's starting to test, it passed, and I think it's telling us about the coverage. So down here is the report on the coverage, which is not that great. I think it's looking at all kinds of things that don't necessarily have to do with this package. So set up the coverage thing is set up not great. And then it's running Flake 8 as well. And on Flake 8, it's going to fail. Yeah, here it's failing on, so the tests passed, but Flake 8 did not pass, and it's complaining about that. And so when we go back, when it's done running this will come back red. And whoever is looking at that and wants to know, so we won't merge this because, well, when I refresh this page, all checks have failed. It's not very granular. It just tells me that the test as a whole has failed, and I'll need to go and look at these logs to say, oh yeah, the tests of the code that passed, but the Flake 8 check that was the thing that failed, and then I can go, if I'm reviewing this code that somebody else wrote, I can say something like, you should go and check your Flake 8 and fix these there, and I can even do things like this allows me to do things like go here and go to this log and this log is long, and just say copy this URL and then say and then whoever is writing this code, presumably not me, because my code never fails, can click on that and say and go, and this will take them straight to that line right there, and they can see that indeed that failed, and see all these comments and fix them and commit that and make the changes. Yes?
Does that mean that big open source projects that rely on Travis for the integration with the others, this is actually public?
This will be public, yeah. You can make it private by paying Travis.
Okay.
And all these logs are going to be, yes, forever and ever are going to be public, which is very useful because you can go and see what it looked like when the code was in state, in a very particular state. What were the failures then? I think it stores all of it. So you can go back and look at things, unless somebody somehow changed the history and things of that sort. So
it's kind of like standard practice then, if you make a pull request to be able to see precisely.
Yeah, and I think it's set up so that I think it's set up even now. I think it's just automatically set up so that when Travis failed, I got an email saying your pull request, it failed, with a link to where I should go and look and so on. So it's really makes everything really easy. You make the pull request, and then if sometimes these tests take a while to run, whenever you get back that report, you'll go and you'll check and so on. Yeah, and most big open source projects use this. It makes your life as a maintainer really easy because you don't have to now pull somebody's code onto your machine, run the tests to see if they pass, and then go back and say, well, no, this failed in the following way. Something else runs it for you, and yeah. Okay, it is time. I'll just mention that the next little bit is about building the docs, which we didn't really get around to, but it's all in that document that I showed you in the beginning. So you can just go from Travis onward, downward, to talk about to look at how the docs are built in this cookie cutter context, including how things are documented, how that doc string that we wrote gets pulled into the website that gets created for the documentation. So there's another system of, Travis can also build your documentation for you and upload that documentation to website whenever you make changes to the documentation. So the sort of continuous integration idea also applies to documentation, not just to testing. Yes?
Do you have an opinion about Travis CI versus Circle? Better?
I'm much more used to Travis because I've used it a lot more. As Chris mentioned, Circle seems to give you more computational resources to work with, but I'm less used to using it. Something about the logic doesn't fit my head quite, and it confuses me. So that's.
It's more like what you're used to, basically.
Yeah, it's a little bit. For me, it's a little bit force of habit. Yeah, that's pretty much it. Except for these additional resources, which seem like a real advantage, I haven't been sufficiently provoked to switch yet to go to Circle CI instead. So, okay, let's take a little break at this point. Let's do like a 10-minute break before the next tutorials. I'll be around so you can come and ask me questions also about this, and hopefully you'll use this next week in something or.